Hey everyone, welcome back. Today, we're stepping into something deeper than usual. Not just quantum physics, but the idea of complexity itself. And here's the real question. How hard is it to create reality? Not metaphorically. Literally. Think about this. You have a quantum system, a bunch of particles, entangled, evolving. Now imagine you want to build a specific quantum state. How difficult is that? How many steps does it take? How much information do you need? How much time? That is what physicists call quantum complexity. At first, this might sound abstract. But it turns out, this idea connects everything. Quantum computers, black holes, space-time structure. And recently we've started to realize complexity might be more fundamental than we thought. So let's break it down. In simple terms, quantum complexity measures how hard it is to transform one quantum state into another using limited operations. Think of it like Lego. Some structures are easy, just a few pieces. Others require thousands of steps. Quantum systems work the same way. Now here's where it gets interesting. In quantum information theory, scientists study complexity using quantum circuits. Each gate is like a small operation. The more gates you need, the more complex the system is. But here's the twist. If you take a random quantum circuit and let it evolve, complexity doesn't just increase. It grows rapidly, then slower, but it keeps growing. Now pause for a second. Because this is important. We're used to entropy increasing, the second law of thermodynamics. But now we see something similar with complexity. Which raises a strange possibility. Is complexity another arrow of time? Now let's change perspective. Instead of circuits, think geometrically. Imagine all possible quantum operations as points in a huge abstract space. Now ask. What is the shortest path between two states? That path is called a geodesic. And in this picture, complexity becomes the length of that path. So instead of counting operations, we measure distance. This idea appears in quantum field theory, many-body systems, and high-energy physics. But things get even more interesting. In dynamical systems, complexity is related to spreading. Imagine applying a small operation. At first, it affects only a few particles. But over time, it spreads across the entire system. Like a ripple. This is called operator spreading. And it is deeply connected to chaos. In fact, the most chaotic systems are where complexity grows the fastest. Now let's zoom out. Circuits, geometry, spreading. These are all different ways of describing the same thing. Different languages, same idea. And physicists are trying to unify them. But here's where things get almost unbelievable. Complexity might be connected to gravity itself. This comes from something called AD/CFT correspondence. In simple terms, a theory of gravity in one space is equivalent to a quantum theory in another. Two different descriptions of the same reality. And within this framework, something strange appears. Quantities like the volume inside a black hole behave like quantum complexity. Think about that. The growth of a black hole's interior might be linked to the growth of complexity. Which leads to a wild idea. Space itself might be built from complexity. Not matter. Not energy. But complexity. Now think about what that means. If complexity keeps growing, does space-time keep expanding? Is the universe a computation in progress? And here's another layer. Complexity doesn't grow forever. Eventually, it reaches a maximum. At that point, the system looks random. But it also becomes extremely hard to reverse. Which brings us to a deep question. Is irreversibility actually about complexity? Because something can be reversible in theory, but impossible in practice due to complexity. Now let's connect this to AI. Because this is where things become very relevant. AI systems also deal with complexity. They learn transformations, compress information, and find patterns. But here's the key difference. Humans try to understand systems. AI simply learns them. So when AI analyzes quantum data, it might discover structures we cannot even describe yet. And this is already happening. Researchers use AI to optimize quantum circuits, discover patterns, and approximate complex states. So now we have two powerful fields merging: quantum complexity and artificial intelligence. And the big question is, can AI help us understand reality itself? Or even more interesting, is reality already a form of computation? Let's go back to where we started. We asked, how hard is it to build a quantum state? But along the way, we ended up asking, what is time? What is space? What is reality? And maybe the answer is not what things are made of, but how hard they are to create. If you enjoyed this deep dive into physics and AI, make sure to subscribe, like the video, and stay curious. See you in the next one.